ACID stands for 4 properties a database should provide to store your data reliably: atomicity, consistency, isolation, and durability. Together, these 4 guarantees are what let you trust a database with something as important as money. Let's use one simple scenario the whole way through. 2 people, Alice and Bob, each with a bank account. Money will move between them, and we'll see exactly what each of the 4 properties protects. The first property is atomicity, and the simplest way to describe it is all or nothing. Say Alice wants to send $100 to Bob. To us, that feels like a single action, but inside the database, it's actually 2 separate operations. Operation 1, subtract $100 from Alice's balance. Operation 2, add $100 to Bob's balance. Both of these together form one transaction, a group of operations that must succeed or fail as a unit. Now imagine the first operation works. $100 leaves Alice, but then the system crashes before Bob is credited. If we stopped there, the money would have simply vanished, gone from Alice and never reaching Bob. Atomicity forbids that outcome. It says, if any part of the transaction fails, undo everything and put the accounts back exactly as they were. So the database reverts Alice's deduction, and it's as if the transfer never happened. That's the promise of atomicity. It detects a partial failure and aborts the whole transaction, never leaving you halfway. The second property is consistency. Consistency means certain rules about your data must always hold true before and after every transaction. In a bank, an obvious rule is that an account balance can never go negative. So before the database moves Alice's $100, it checks that Alice actually has at least $100. If she doesn't, the transaction is rejected and never carried out. Consistency is what makes the data trustworthy. It guarantees the database only ever moves from one valid state to another valid state. The third property is isolation, and this is the hardest of the 4 because it deals with many transactions happening at the same time. The core idea is simple to state. No transaction should be allowed to act on the half-finished results of another. Let me show why that matters with the second transaction running alongside the transfer. Imagine a family audit. One transaction, call it T1, wants the family's total money, so it reads Alice's balance, then reads Bob's balance, then adds them together. At the same time, transaction T2 is transferring $100 from Alice to Bob. Let's say Alice starts with $500, Bob starts with $300, so the true family total is $800, no matter how the money moves between them. Now watch what happens if their steps interleave in a bad order. First, T2 subtracts $100 from Alice, so Alice now shows $400. Next, T1 reads Alice and sees that $400. Then T1 reads Bob, but T2 hasn't credited him yet, so Bob still shows $300. Now T2 finishes by adding $100 to Bob, making him $400. Finally, T1 adds up what it saw, $400 plus $300, and reports the family total as $700. The audit is now wrong by $100, money that really exists but was counted while it was mid-flight between the 2 accounts. Isolation is the property that prevents exactly this. It guarantees each transaction behaves as if it ran alone, never seeing another transaction's partial in-progress changes. The simplest way to achieve this is called serializability. Lock the entire database so only one transaction runs at a time, start to finish. That works perfectly, but it's slow and costly because everyone else has to wait their turn. So real databases use smarter, more efficient techniques to get the same effect without freezing everything. Either way, the goal is the same. Give every transaction a pseudo-view where it feels like it owns the entire database by itself. The fourth property is durability. Durability means that once a transaction is committed, once the database has confirmed it's done, that data will never be lost. Not to a crash, not to a power outage, not to a server suddenly dying. Databases achieve this in a couple of ways. One is replication, keeping copies of the data on more than one machine, so if one fails, another still has it. Another is a write-ahead log, where the database first records what it's about to do onto permanent storage before actually doing it. If the power drops midway, the database reads that log when it restarts and finishes the job, so nothing committed is ever forgotten. So let's quickly recap all 4. Atomicity? A transaction happens completely or not at all. Consistency? The data always obeys its rules and stays valid. Isolation? Concurrent transactions don't step on each other's half-finished work. Durability? Once it's committed, it's saved for good. One important note. These 4 properties stay constant, but how a database implements them changes depending on the application and its read and write patterns. The real value of ACIC is that it lets you build on top of the database without constantly worrying about crashes, partial failures, and race conditions. But that safety comes at a genuine cost in speed and complexity. So be aware of that trade-off before you reach for an ACIC database. For something like a high-traffic social media app, those strict guarantees may not be worth the price. Choose them where they matter most, where, like Alice sending money to Bob, getting it exactly right is worth everything. If you want more clear, example-driven breakdowns of system design, follow the channel.